Why randomness isn't what we thought. For a long time, randomness felt like ignorance. If outcomes were unpredictable, it meant we lacked information. Chance was just a placeholder for what we did not yet understand. This assumption shaped how science treated uncertainty. Randomness was something to eliminate, gather more data, improve measurements, refine models. With enough knowledge, randomness would disappear and certainty would take its place. Scientists operated under the conviction that unpredictability was always provisional, a temporary state reflecting incomplete knowledge rather than a permanent feature in nature. This view made randomness a problem to be solved rather than a phenomenon to be understood on its own terms. To understand why this belief still matters today, we need to revisit how predictability earned trust. Classical physics delivered astonishing accuracy. Given enough information, the future could be calculated precisely. Randomness appeared only when information was missing. Newton's equations predicted planetary positions centuries in advance. Engineering calculations yielded bridges and machines that worked exactly as designed. Every success reinforced the idea that with sufficient data and careful analysis, anything could be predicted with certainty. The universe seemed fundamentally deterministic, a clockwork mechanism following precise laws. This success created confidence. If nature ever seemed random, it must be because we were not looking closely enough. Deeper understanding would restore order. Uncertainty would collapse into law. When dice appeared random, it was only because tracking every air current and surface texture was impractical, not impossible in principle. When gas molecules moved chaotically, it was because monitoring trillions of particles exceeded human capability, not because their motion was fundamentally unpredictable. Randomness was always attributed to missing information, never to nature itself. But as physics pushed into smaller scales, that promise broke. Even with complete information, outcomes refused to settle. Identical experiments produced different results. Probability remained stubborn and irreducible. When physicists fired single electrons at detectors under carefully controlled conditions, the outcomes varied randomly despite every effort to make the setup identical. Quantum systems exhibited genuine unpredictability that persisted no matter how precisely initial conditions were specified. The randomness could not be eliminated through better measurement or more careful preparation. At first, this was blamed on hidden variables, unknown influences waiting to be discovered. Surely randomness was still a mask, but every attempt to remove it failed. The uncertainty was not hiding anything. It was fundamental. Experiments tested whether hidden properties might determine outcomes behind the scenes, but the correlations observed were inconsistent with any local hidden variable theory. The randomness was not a sign of incomplete description, but an irreducible feature of quantum mechanics itself. Nature was genuinely indeterminate at the quantum level. This was the first crack in a comforting idea. Randomness was not a symptom of ignorance. It was part of the universe's design. This realization challenged the entire philosophical framework within which science had operated. If outcomes were not determined by prior conditions, then what did causality mean? If perfect knowledge still left room for uncertainty, then what was the nature of physical law? The implications rippled through every domain of physics and beyond. And once that possibility was taken seriously, chance stopped looking like a mistake and started looking like a rule. Randomness was not nature's failure to be predictable, but nature's way of operating. The universe incorporated genuine indeterminacy as a fundamental feature, not as an artifact of insufficient knowledge or measurement limitations. At first, physicists resisted this conclusion. Accepting fundamental randomness felt like surrender. Science was built on explanation, not acceptance. If outcomes were truly probabilistic, then prediction had limits no amount of effort could overcome. The entire scientific enterprise seemed threatened. How could science make progress if the universe itself was fundamentally unpredictable? The resistance to probabilistic interpretations was fierce, with prominent physicists refusing to accept that nature operated through chance at its deepest level. So alternative explanations were proposed. Hidden mechanisms, deeper layers of determinism operating beneath perception. Randomness, it was argued, only appeared because something important was still missing. Perhaps there were variables inaccessible to current experiments that would restore determinism, if only they could be measured. Perhaps the probabilistic framework of quantum mechanics was merely provisional, awaiting replacement by a more complete theory that would eliminate randomness. Scientists search for ways to preserve classical determinism, to find the hidden clockwork beneath quantum unpredictability. But experiment after experiment closed those escape routes. Tests designed to expose hidden variables failed. Correlations appeared where no signal could travel. Outcomes depended on probabilities alone, not on unseen instructions. Randomness remained even when every known factor was controlled. Bell's theorem and subsequent experiments demonstrated that no local hidden variable theory could reproduce quantum mechanical predictions. The randomness was genuine, irreducible, built into the fabric of nature. There was no deeper deterministic layer waiting to be discovered. This created a deep conflict with intuition. How could the universe be lawful and unpredictable at the same time? Laws were supposed to produce certainty. Rules were meant to fix outcomes. Yet here were rules that described distributions, not destinies. Quantum mechanics provided precise mathematical laws that governed probabilities but left individual outcomes undetermined. The theory made perfect predictions about statistical distributions, while remaining completely silent about which specific outcome would occur in any single trial. This was profoundly different from classical physics, where laws determined exact trajectories and randomness only reflected ignorance. As this understanding spread, probability took on a new role. It was no longer a tool for managing ignorance. It became a fundamental feature of reality. The universe did not choose exact outcomes. It chose ranges, likelihoods, and tendencies. Physical laws specified probability distributions rather than definite results. The wave function described not what would happen, but what could happen, and with what likelihood. Nature operated through propensities rather than predetermination. This transformed probability from an epistemological concept about what we know into an ontological one about what exists. Emotionally, this was unsettling. It suggested that even perfect knowledge would not grant control. The future was not written in detail. It was sketched in probabilities, waiting to be resolved by events themselves. This violated deeply held intuitions about how reality should work. If even the universe itself did not know what would happen next in certain situations, then certainty was unattainable in principle, not just in practice. The discomfort this generated was not merely intellectual, but existential, challenging assumptions about predictability, control, and the nature of existence. Randomness was no longer an error to be corrected. It was something the universe actively used, and that realization was leading toward a deeper question. If chance is fundamental, what does that say about cause, control, and meaning? Does causality still make sense if causes do not determine effects? Can there be purpose or direction in a universe that incorporates fundamental randomness? These questions force a complete rethinking of basic concepts that had seemed settled. The conflict deepened when physicists realized that this randomness followed strict rules. Outcomes were unpredictable, but not arbitrary. Probabilities were precise. Patterns emerged across large numbers of events with unwavering reliability. While individual quantum events were random, the statistical distributions they produced were completely lawful and reproducible. Quantum mechanics made extremely precise predictions about aggregate behavior, even while remaining silent about individual cases. The randomness was structured, constrained, governed by exact mathematical principles. This buildup revealed a strange duality. The universe was unpredictable in detail, yet stable in aggregate. Individual events resisted forecasting, but collections obeyed law-like behavior. Chance and order were not opposites. They were partners. A single radioactive atom might decay at any moment unpredictably, but a large sample would decay at a precisely predictable rate. Individual photons struck a screen randomly, but millions of them produced perfect interference patterns. Randomness at the microscopic level gave rise to regularity at the macroscopic level through the law of large numbers. This forced a reframing of causality. Causes no longer guaranteed effects. They shaped likelihoods. The universe did not promise what would happen. It promised how often something could happen. Reality became statistical. Causation meant influencing probability distributions rather than determining outcomes. A cause made certain effects more or less likely without fixing them in advance. This probabilistic causation was still lawful and predictive, but operated through tendencies rather than necessities. Emotionally, this was difficult to accept. Humans crave certainty. We want causes to deliver outcomes. But physics was offering something colder and more honest. The universe operates on tendencies, not intentions. Nature does not guarantee specific results, but specifies probabilities. The statistical character of physical law felt unsatisfying, incomplete, as if science had given up on truly understanding nature. Yet the predictions worked with unprecedented precision, suggesting that this probabilistic framework captured something true about reality. As this idea settled, it revealed why randomness could be useful. It allowed flexibility. It prevented rigidity. It enabled systems to explore possibilities rather than follow a single path. Randomness was not noise. It was freedom within constraint. In a purely deterministic universe, every outcome would be fixed from the beginning, leaving no room for genuine novelty or adaptation. Fundamental randomness provided a source of variation that could be acted upon by selection and optimization. It allowed systems to sample different possibilities, to innovate, to avoid getting trapped in fixed patterns. Randomness became a creative force rather than mere chaos. By this point, chance no longer looked like ignorance. It looked like structure, a built-in openness that allowed complexity, adaptation, and novelty to exist without violating underlying laws. The randomness was not featureless noise, but highly structured indeterminacy, constrained by precise mathematical rules. It provided just enough unpredictability to enable interesting dynamics, while maintaining enough regularity to allow stable patterns and reliable predictions at appropriate scales. The question was no longer whether randomness was real. It was why the universe chose to include it at all. What purpose did fundamental indeterminacy serve? Why would nature incorporate genuine chance rather than operating through perfect determinism? The answer seemed to be that randomness was essential for certain kinds of complexity and creativity that could not exist in a rigidly predetermined universe. The climax of this story is a reversal that still feels uncomfortable. Randomness is not the absence of law. It is how law operates at its deepest level. Physical laws do not specify what happens, but what can happen, and with what probability. The rules themselves are probabilistic, governing distributions rather than individual outcomes. This is not a deficiency, but the fundamental character of natural law at the quantum level. Once this is understood, unpredictability stops feeling like failure. The universe is not undecided because it is confused. It is undecided because it is structured to allow multiple outcomes. Laws do not dictate events. They constrain possibilities. Within those constraints, genuine indeterminacy remains. This is not lawlessness, but a different kind of law, one that shapes probability spaces rather than fixing trajectories. The universe maintains order and regularity through statistical laws, while preserving openness at the level of individual events. This insight reshaped physics and philosophy alike. Determinism was replaced with consistency. The universe became reliable without being rigid. Patterns held, even when details varied. Order survived, not despite randomness, but because of it. Science learned to make precise predictions about statistical distributions, while accepting that individual outcomes remain fundamentally unpredictable. This probabilistic framework proved extraordinarily successful, underlying quantum mechanics, statistical mechanics, and much of modern physics. More deeply, it reshaped perspective. Control has limits not because knowledge is weak, but because openness is fundamental. The future is not fixed in advance. It emerges, guided by probabilities rather than commands. This realization has implications beyond physics, affecting how we think about free will, determinism, and the nature of time. If the universe itself does not predetermine all outcomes, then the future is genuinely open in ways that deterministic frameworks could never allow. Today, this understanding underpins modern science. It explains why prediction works statistically, why systems remain stable while events fluctuate, why complexity can arise without precise planning. Every field from quantum computing to evolutionary biology relies on this insight that randomness is fundamental yet structured. The probabilistic character of natural law enables both the stability necessary for order and the flexibility necessary for novelty. Randomness is not what we thought. It is not ignorance waiting to be erased. It is the universe leaving room for possibility. This represents a profound shift in how we understand nature, from a clockwork mechanism where everything is predetermined to a probabilistic framework, where the future remains genuinely open within the constraints of natural law. Accepting fundamental randomness means accepting that perfect prediction is impossible in principle, not merely in practice, and that this unpredictability is a feature reality itself rather than a limitation of our knowledge. So, what do you think? Are we repeating the same mistake again? In our current pursuit of understanding consciousness, artificial intelligence, or cosmic evolution, are we once again assuming that apparent randomness must hide some deeper determinism? Are we still seeking to eliminate chance rather than recognizing it as fundamental? The question remains open, inviting reflection on whether science has truly absorbed this lesson or continues to resist the idea that the universe might be genuinely probabilistic at its core. Why